Welcome to Making Stuff with Chris DeHut. Today we're going to take a look at the PWM signal, Pulse Width Modulation, on the Raspberry Pi PICO. The PWM signal is the digital computer's way of simulating or mimicking an analog output. Now, most microcontrollers and computers cannot generate an analog output, meaning a variable voltage output. Our outputs are strictly on or off and at the system's voltage, 3.3 volts in the Raspberry Pi PICO world. Now, before we get into the programming of it with MicroPython, I'd like you to see what a PWM signal looks like on the oscilloscope as well as on an LED. Over here on the oscilloscope, you can see I've got a 1000 Hertz cycle going. And this is what a PWM signal looks like. If you're not familiar with oscilloscopes, down here is 0 volts, up here is 3.3 volts, according to the settings that I've set on my dials. Now what we're looking at is time from left to right, voltage bottom to top. So 0 volts, 3.3 volts, and then this is time going to the right. And what we're seeing, this would be one cycle from here to here would be one cycle. And you'll see that half the time it's on and the other half is off. And we refer to that as 50% duty cycle. 100% duty cycle would mean that it's always on, and a 0% duty cycle would mean that the signal is always off. Now, for a comparison, what we're going to do is take a look at an analog signal. And we'll see that specifically on the oscilloscope, but I want you to understand how I've got this set up, both on the Raspberry Pi as well as on the oscilloscope. Now, the PICO is playing no part in this other than providing voltage over to a trimmer potentiometer. And this is set up or configured as a voltage divider. So as I rotate this, we'll be changing the voltage from 0 volts to 3.3 volts. So I'll be tuning that, and we'll see the result over on the oscilloscope. Now, I've also got a schematic that I've created in Fritzing so that you can clearly see what is actually shown here. And here is my probe for the oscilloscope. This is the ground clip for the oscilloscope on our ground wire. And then this is 3.3 volts coming out of the PICO. So here we're going to measure the voltage, and that's what you'll see on the oscilloscope. Okay, this is analog voltage output, and I'm rotating the potentiometer to see that signal change. So there's 0 volts. I'll raise it up, and that is now 3 volts. So back down 0, back up 3 volts. That gives us infinite control between 0 and 3 volts. That is the difference between what an analog signal looks like versus a digital signal. In our case, for today's discussion, a PWM signal. Now, for reference, I always refer to the book published by Raspberry Pi Foundation. This one in particular is Getting Started with MicroPython on the Raspberry Pi PICO. If you don't have this, I highly recommend you download it and have it available. It's a tremendous resource. The other resources that I use when working with the Raspberry Pi PICO is the Raspberry Pi PICO datasheet, the Raspberry Pi PICO Python software development kit, and the actual chip, the RP2040 datasheet for the Raspberry Pi PICO. These are all excellent references. They're free of charge and published by the Raspberry Pi Foundation. Now, the one that we're looking at specifically today, we're talking about the PWM signal. Now, on page 101, what we're looking at specifically for PWM is to determine which pins we can use, and more importantly, which pins we can use at the same time. We cannot use PWM A, number 0, and PWA number 0 over here at the same time. We can use other combinations, but we can't use those at the same time because they share the same resources. If we did use them at the same time, they would have to run at the same frequency and duty cycle. So just be sure if you're using multiple PWM outputs to select from different groupings and not matched pairs such as shown here. Before we get into the coding, let's take a look at the circuit for our example program, which is using an LED. And it is also providing us with an area to hook up the oscilloscope. Now over here we're using GP number 2, which is pin number 4, the physical pin number 4. That connects to the long leg of the LED. Long legs are always positive in many regards. The flat side of the LED connects to a resistor, which comes back to the ground rail and then connects back to the Raspberry Pi PICO at a ground pin. Now for the oscilloscope, I've got the probe connected to the long leg of the LED, and that's the signal we'll actually be seeing, and then the ground for the probe is connected to the same ground rail. Now up here on the actual breadboard in the real world, we've got the same thing going on. You see 2 wires here that were for our analog signal. This is the wire off of GP number 2 coming over, connects to the long leg of the LED. Flat side of LED always goes towards negative. So that's connected to ground via this 220 ohm resistor on the ground rail and then back into the Raspberry Pi PICO on a ground pin. And here is the ground connector for the oscilloscope and the probe for the oscilloscope. Now we can take a look at the program itself. Now we're going to load a couple of libraries. Import machine is the machine-specific library for how MicroPython deals with the unique differences between each type of microcontroller, such as a Raspberry Pi PICO or an Arduino, etc. UTime is the library for your time-based stuff, and in this particular part of the program, we're really not utilizing it, but we will in further iterations. Now, the UTime is identical to time, except for it's the MicroPython version of it. Now, the most important line that's coming up is this one right here, and of course the next one. But PWM underscore sig equals machine.pwm is essentially creating an object within our program from the constructor of the PWM signal in the machine library. And in this case, we're setting it up on machine.pin number 2, GP number 2, as I referenced in that previous bit of information out of the manual. So that creates the object PWSig that we're going to use for our pulse width modulated signal on that output pin. The next item is our frequency. Now we're going to set that frequency in this example at 1,000, and that's a good starting point. If you set it too low, say you set it to 10 or 100, and you've got a device such as a lamp or an LED, you might see flicker. So you want to set it high enough so that you don't see that flicker. If you're controlling an electrical motor, such as a hobby servo or a conventional motor, you don't want it too low, because if it's as the LED is flickering, imagine a motor being started and stopping that rapidly. It could be very punishing to the motor and all the circuitry in between. Furthermore, you cannot go too high on that frequency, because the MOSFETs, the devices that are actually controlling the high-powered voltage and amperage controlling the motor, probably can't switch on and off all that fast. So they really are dictating what your max frequency is for a motor controller. So you will have to check the data on your motor controller to see what the max frequency allowable is. If you don't know, start at 1,000, go up or down from there, and monitor the behavior for results and see, make adjustments to make it better if you can. The next element that is very critical is the duty cycle. Now, the duty cycle is that on time of that cycle within our frequency setting. So as we look at that on the oscilloscope, our duty cycle is this upper time right here. Now, the downtime here is the off, this is the on. So in this particular example, I'm running at a 50% duty cycle. Now, one of the things getting into these numbers and conversions to duty cycle, frequency, hertz, and all this fun stuff, it can be a bit confusing. So what I've done in this particular example is I've broken it out so that we can work in a term that we're all familiar with, a percentage. And in this case, the maximum duty cycle we can have is 655.36 individual settings. Now, because it's a computer, it starts at 0 and counts up to 655.35. Now, that would be 100% on or 100% duty cycle, and therefore 0 would be 0% duty cycle. Now, let's say I wanted to have 5% duty cycle, just barely on. Well, I would take that 655.35 and multiply it times 0.05, and that would give me 3276. So I would set that as my duty cycle. And likewise, if I wanted it at 25%, 50%, 75%, I would just do the multiplication. This would show me the results, and this is the percentage that we would get. So in this case, in our example, I've set duty cycle at 655.35 times 0.5, or 50%, and we've established that as the duty cycle, and then we've set the duty cycle on the PWM signal object to that duty cycle value. So we just take this value and put it in there. And that controls how much output we're going to get from this duty cycle or from this PWM signal. So if everything was linear in an ideal world at 50% duty cycle, the LED in our example here would be at half brightness. And if we had a motor hooked up, we'd be running at half speed. It's going to be pretty close to that if all the circuitry is good, but don't expect absolute perfection in that regard. Now let's take a moment to look at how the duty cycle affects both the signal on the oscilloscope and the brightness of our LED. So the first thing we'll do, let's reduce our signal down to 5%. So we'll go ahead, run that. All right, now we look at it on our oscilloscope, my time machine, and we'll see that we've got a very small amount of on time versus a lot of the off time. If we look at our LED, we'll see that it's glowing rather dimly. It's not very bright. Now, it's kind of hard to say because you don't have anything to compare it to, but we'll see here in successive values that we're going to set to. So that was at 5%. Let's go to 25%. If we look back over at our oscilloscope, we'll see that our on time got wider and our LED's getting brighter. Now let's go to 50%. We're back to our original example that we started with, 50% on, 50% off, and our LED's gotten a little bit brighter again. We'll go up to 75%. Now you can see in our signal, on is almost all the way across, almost 100%, and our LED got even brighter yet. Now we'll go for full on. Actually, I'm going to stop a little bit short, but I'll explain that in a minute. I'm going to go about 98% for my on time. What I want to do is for you to be able to see on the oscilloscope how we've got our on time all the way across and we just drop down. Now at 100%, the line would just be solid across the top. Over here at the LED, you can see again, it's even more bright. For comparison, we'll stop this one, set it back to 5% or even 2%. Run that, and you can barely see the LED glowing at all. Now I've changed my duty cycle back to 50%. We can see that on the oscilloscope, and we can see that on our LED. And you'll notice that the LED is solidly lit. It looks perfectly fine. No flicker or anything like that. So now let's change our frequency and see how the behavior changes. So we'll go from 1,000. I'll stop it now. We'll go to cut that in half to 500. And you'll notice over on the oscilloscope that the signals got wider in that same time frame, so they're longer on and longer off because it's going at half the frequency. But we still don't see any flicker on the LED. So we'll go stop this. We'll stop this. We'll change it down to, let's go to 50 and see if we can see any flicker at all. Still no flicker on the LED. Camera might be picking up a bit more. And as you can see here on the oscilloscope, our signal got so long that it's actually exceeding what I can show on the screen at this time base. So I'm going to adjust it down so we can see the signal. And I'm going to make it even smaller yet. Again, all I'm doing is changing how much time is represented by each one of these lines on our graph. Finally, we'll go down to 10 hertz, or 10 times per second, and we'll see if that creates the flicker. Now that's an obvious flicker, and you would definitely not want to look at that for any period of time. It'd just irritate your eyes. Now imagine a motor being turned on and off at that frequency. It would be very damaging to all the power circuitry as well as the motor itself probably, because it's constantly starting and stopping. So that's the effects of changing our duty cycle too low. Going too high would be harder to demonstrate or show such that you couldn't see a visual representation of it, so it's hard to demonstrate the ill effects of a high frequency. But again, if you don't know, start at 1,000, work your way up or down from there. Another example, just so that you understand how fast this can actually go. Earlier, we were running a base frequency of 1,000. Right now, I've changed it to 10,000. LED, you wouldn't see any difference on that. Here we can see that it's running at 10 kilohertz or 10,000 times per second. Well, let's see how fast the PWM signal can go. That's at 10,000. So I'm going to change it to 100,000. And we look at that on the scope. We can see that it is just short of 100,000 here. Of course, the LED doesn't look any different. We'll try to go faster and see if we can get more frequency out of it. That's pretty darn fast. All right, now at that point, we are at nearly 500,000 hertz, or 498,000 kilohertz. So that's really, really fast. And you're now starting to see some decay on the actual signal. We get some ringing on the off and ringing on the high. So the signal's starting to degrade, but nonetheless, it is outputting a pretty decent 500,000 hertz PWM signal. And again, with the LED, you will not see any difference there. Now, the last thing I want to show you with PWM, which adds a little pizzazz to it, and it gives you that true variable speed control. What we're going to do with this example program is ramp up the brightness of the LED and then dim it back down slowly so that we can accelerate a motor and decelerate a motor, if you see what I'm getting at. And of course, these ramp up and ramp down effects can be pretty neat for various lighting situations as well. As far as the programming goes, it's quite straightforward. We've got everything is pretty much the same at the top. We're going to start with our duty cycle at 0. Then we're going to enter a loop to ramp up the brightness of the LED. So starting at 0 means it's off. So we'll get into a while loop where we're going to increment the duty cycle up by one bit every time through the loop. We'll set the PWM signal's duty cycle every time through the loop, and then we'll just slow it down a little bit so that we can actually see it happening. So once we get to full brightness, then we'll turn around and we're going to start again at 655.31 and then count down to 0. So here we're minus equals 1, counting down, setting our duty cycle, and again sleeping. So we'll see the effect of this on, first let's look at it on the LED. So we'll run it. Here you can see it ramping up and now dimming down. Very smooth, no flicker, no jitter, so it's a nice signal up and down. Now let's look at it on the oscilloscope. Here you'll see it going full on, and then now full down. Again, full up, 100%, back down, 0%. So that is how you would do fading and variable speed control with an electric motor. Of course, some motors you don't need to accelerate up and decelerate down, but bigger motors, certainly that's a good thing to do. Otherwise, you can cause a number of problems with your drive circuitry. I've used PWM signals on various microcontrollers for many years now, and they've been very, very beneficial to many of the projects I've worked on. So I would recommend, if you're a good tinkerer, a good maker, you should learn about the PWM signal and experiment with it so that you can utilize it in your projects. The other thing I'd like to mention, if you like this video, please subscribe to the channel. That will help secure its existence in the future. And if you like the video, give me a thumbs up. I'm Chris DeHut for Making Stuff with Chris DeHut. Thanks for watching.